second. Then if we look at the frequency for the first wave, it would be 2 over 1. Yes, because there's 2 waves in 1 second. So that is 2, and the unit for frequency is hertz. 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 Right? If we look at what the frequency would be for the second wave, then there is 1 wave in 1 second. So there is 1 hertz is the wavelength. Not the frequency. Does it make sense? Okay, so I'm giving you a crash course in grade 10 waves now. Okay, ma'am, why do we need it? Blah, 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 blah. They don't ask this that often in this chapter, but they do sometimes ask it. And it will be silly of me not to teach you this. All right. Okay, so I'm just going to say again, what is frequency? Frequency again is or how low. Okay, something is. And what that has to do with is how many waves there are per second. So if there is not a lot of waves, then it's very low. If there's a lot of waves, then it's very high. Okay. Then the next thing that we can look at is wavelength. Okay. Wavelength. If you don't have any space, you can go on at the last page or the back of this page. Okay, right. Now, let's pretend these are sound waves sound waves that we are looking at. Okay. Now, the speed of sound normally, in normal air, is around about 340 meters per second. That's normally how fast it moves. You would have done, if COVID did not exist, you would have done this practical in grade 10, but you didn't. But it changes depending on the weather. If it's colder, then it moves slower. If it's warmer, it moves faster. Yes? Mm-hmm. All right. So, let's say I want to see, okay, this wave, what is the length of one wavelength? Okay, I want to know how long one wavelength is. Then we go to this formula. Speed is frequency times lambda. Lambda. Okay. So I'm going to break this down for you. We just spoke about frequency. What is frequency again linked to? Frequency is linked to the, so this is frequency, and it is linked to the pitch. Okay, I don't want to ask this even because I'm recording, but you know there's some teachers that you just feel, if they speak, you just want to do like this after a while, your ear, yes? All right, and then do you sometimes say, that teacher's voice is pitchy? Or that person's voice is pitchy? Do you say something else in Sutu? No, what do you just say? Wat is goed? Wat betekent dit? All right. Okay, but what you actually want to say, the thing the concept that you're describing is it is pitchy, the voice. Okay, so that is frequency. Then here, okay, V is speed. You all know that, yes? You did a whole chapter on speed. Then this thing there is an upside down Y. It's actually a bit curvy. It actually looks like this. Okay, but obviously I'm not going to draw it like that. Okay, that is lambda. Lambda. And that is the wavelength. Wavelength, how long a wave is. Did your teachers at extra class speak about this? Oh, okay. All right. So wavelength is measured in meters. Length, meters. Yeah, I know. Load shedding. Just underneath the wavelength, you write meters. Meters. M. Alright, so wavelength, length is measured in meters. Okay, so we can take that formula. That formula is on your data sheet. You just need to know what it stands for. And, sorry, we can go determine what is the length, the wavelength, the lambda of one wave. Alright, so I want you to write there 1. Okay, for wave 1, we're going to determine the wavelength. So that is 340 is equal to, 340 is equal to, then what was the frequency for the first wave? 2. So it's 2, that frequency you put in 2. And now you want lambda. Okay, and then you get lambda to be what? 170 what? Meters length. Lambda is the wave length. The wave length. Okay. Right, then the second wave. So 2, second wave. Again, if we consider this to be sound waves, the speed will remain the same, 340. That frequency was 1 hertz times lambda, and then lambda is 340 meters. Okay, so what we can conclude from there. Okay, can you see the first one that has 2 hertz frequency, the high frequency, had a smaller wavelength, yes? And the one that has a lower frequency had a bigger wavelength. So what relationship, mathematical relationship is there between the two? Between frequency and wavelength? What's the mathematical relationship between the two? We saw the one that has a bigger frequency has a smaller wavelength. And then the one that has a smaller wavelength, a smaller frequency, has a bigger wavelength. What's the mathematical relationship? They are inversely proportional to one another. They are inversely proportional to one another. Mooi, mama. Inversely proportional. Right. Are you still with me? Sort of. Okay. Then I'm going to go on there at the top. Okay. So we can change. We've done so far 2 things that we can change. We can change the number of waves, so the frequency, or we can change the wavelength. How long is one wave? Okay. Now the next thing that we can change is the amplitude. Amplitude. Declan, amplitude sounds like what?
Sounds like.
No, amplitude sounds like
Amps on this for
like amps. Explain to people that don't know what is amps.
amps. And that is for like speakers and stuff.
Speakers. So if you want to make some, what does an amplifier do? An amplifier speaker, it makes your voice or your music or your whatever to be louder. Okay. Now the same thing in amplitude has to do with the loudness of a wave. Okay. How hard or soft a wave is. Okay. So if we have, let's say we have a normal wave here. Let's make it 2 waves. 1, 2. Then in a wave, there where we have our middle point, it's called the equilibrium position. That is called the equilibrium position. Okay, so equilibrium position is your middle line, your resting position. Okay, now we can, if we make it softer, okay, so I tell you, please turn down your music, but you still want it. Okay, you make it softer. Then what you do is from your equilibrium position, your amplitude, your how big or how high a wave goes will be smaller. So now we have a smaller wave, a smaller amplitude. So I still have two waves. The wave length is still the same. Okay, so I'm going to zoom in there. So what we refer to the amplitude is this part here. The part from its equilibrium position is smaller. That is the amplitude. Okay, and if we make this louder, then we would still have two waves. We're not changing the frequency, we're not changing the length. Still have two waves, but now it's going to be a high amplitude or higher. Alright, chap. Okay, so that is your background information from grade 10. I'm just going to revise them quickly. We have frequency. Frequency is how many waves we have, and that is linked to the pitch. No. Then we have the wavelength. Okay, how long or how short the wave is. And frequency and wavelength or lambda is inversely proportional to one another. Okay, and then we have amplitude, and amplitude has to do with how loud or how soft a sound is. It has nothing to do with the pitch, nothing to do with how many waves. It is just how loud or how soft. All right, now we're going to come to the Doppler effect, and that is what I started this lesson with. I said when you drive past a car or car drives past you, you hear meow. Okay, and why do you hear that? Because there's a change in the way we observe the sound. Do you think the person that, let's say it's an ambulance, it goes, pew, wee, wee, wee. Do you think the person inside the ambulance hears, pew, wee, wee? No, they hear the same things. Okay, so that sound does not change when the car drives. It's just, we observe it, we see it as being changed, because we stand still and we're not going with the sound. Okay, right. So, I'm going to read and then explain further. It says there, yes. No, so it will, the 340 depends on the temperature of the day and where you are, like are you at sea level or you're up in the air, whatever. They normally tell you what that is, or they will give you other information and ask to calculate it. Okay. But it's normally around about there. Right. That has to do with the air pressure. The air pressure will influence the sound a bit. Okay. Ooh, I want to say something further. So that is the sound of speed, more or less, in air. Okay. When you, sometimes I will go out of the class and you feel it's a good opportunity to lay on your arms, né? And put your ear on the desk. And then, before you even see me, you hear me coming back. Okay, so you're like, oh, man, it's back here, pretend we're working, what. Right. Why does that happen? Why do you, when you put your ear on the table, you hear me before you see me? Say again?
Vibrations.
Okay, and sound is just vibrations. Okay, so sound will travel faster through solid particles. Okay, and it will also travel fast between water particles. Okay, so why does that happen? Gas particles are far away from each other, right? So how does sound propagate? Propagate is the fancy word. How does sound travel? It travels by colliding of particles. Okay? Now if the gas particles are far away, it takes a while before it hits and go on to the next one, on the next one. Where in solids, the particles are tightly packed together. So they collide much faster. Okay, so they do sometimes ask you, what is the speed of sound of a dolphin in the water? Okay, a dolphin makes a sound. Then you would know, in a liquid, the speed will be greater than in a gas. Okay, so then your answer that you must get should be in the thousands or 2000s, it depends on the question. Alrighty, so I'm going to go up and explain. It says, when a vehicle drives past you, you will hear a change in frequency or change in pitch in the sound of the vehicle. Why? The speed of the source, now the source is the thing that makes the sound. The ambulance, the car, the dolphin, the whatever. The speed of the source is slower than the speed of sound, and that specifically will be in air. Okay. How fast does a car in town normally drive? 60, 80 kilometers per hour, depends who's driving. Ne? Let's say it is 60 kilometers per hour. That's the speed limit in town. How will we convert that to meters per second? Divide by 3.6, and that gives you what? 16. Okay, so that is the speed that the car travels. 16 meters per second. That's quite fast. Okay, and so that is the speed of the car. The speed of sound in air, we said, is normally plus minus 340 meters per second. So can you see that the speed of sound is much faster than the speed of the car? Okay, right, so there's a difference in the speed. So they say there, the speed of the source, the speed of the car, is slower than the speed of sound in air for that day. Right. Now, what change in frequency do you observe? Do you hear? They say when the source and the observer is the person that hears it, and the source is the person that makes the sound. When the source and the observer move towards each other, they come closer to one another, then the frequency that is observed is higher. No, it's higher. Then, when they move apart, so you're still standing and the ambulance is moving away, you hear right? So it moves away, then the frequency would be lower. Okay, now why is that? And that's what this whole chapter is about. As you can see, here we have an ambulance and there's two people. There's someone at the scene of the accident and you are standing here. Now let's say the ambulance started there. Now when it travels to the right, it makes a sound. So it gives off sound waves. Now as it is traveling, okay, it gives out sound waves, but it is also traveling towards the sound. Okay, so towards the part of the sound wave. So what happens is it gives you more sound waves, and these sound waves are compressed together because it's moving in that direction. So it's compressed together. You can see here in that time frame there's a lot of waves. What is a lot of waves in a certain time? It's a high frequency. Yes? Alright, and if you take that same time frame, this side, you see there's a lot less waves. Okay? So it's a lower frequency. So this is the whole concept. This is the whole chapter. If you must know that if something moves towards, then the waves will compress, get together, and the frequency will be higher. When it moves away, the waves go apart and the frequency is lower. Does it make sense to you? Okay. The same concept is explained here at the bottom. Just a bit more scientifically. Tell you there. In the diagram, the sound source moves from S1 to S2 and produce sound fronts of 1 to 4 respectively. So it started there and now it's moving to the right. Same thing here, it started and it's moving to the right. Okay, so it produced that sound wave, then that one, then that one, then that one. So it's moving out the sound waves. Right, for listener 1, L1, the wavelength spread out and the frequency decreases. Therefore the pitch is lower. Okay, and for listener 2, the wavelengths are compressed, the frequency increased, and therefore the pitch is higher. Now they're going to ask you to explain this concept in words over and over again, and that is your answer that you give. This will count 2 marks, 1 for this concept and 1 for this concept. Okay, so they're going to ask, is the pitch observed by listener 1 lower or higher? Then you're going to say, okay, well, listener 1, where is it? Okay, it moves away from it, so the wavelength spread out, the frequency decreases, the pitch is lower. All right, anyone's got a question there? Ma'am, you need to explain again? Yes? No? Siamo? Was ek explaining? But I'll explain it more and more and more. Okay. Now this chapter has one definition. Okay. So do you think they're going to ask this definition? Yes. Okay. So please go study this off by heart. Okay. Now this definition is not easy peasy. Okay. It reads as follows. The change in frequency or pitch of the sound detected by the listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. Okay, that is a mouthful. So, what is the Doppler effect? A change in frequency of the sound detected because the sound source and listener have different velocities relative to the medium of sound propagation. Yes. Propagation is how it is planted forth, how it is produced, how it is transferred. So, if we say, didn't you do history in grade 8 and 9? Did you do the Nazis and whatever? Yes, and then they said, what was the propagation of Adolf Hitler in this thing, blah, 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 blah. Oh, yeah, propaganda. It's the same basis word. So what was the propaganda? What was the force? What is the drive? What is the message that is planted forth to the next person reading it? Same thing is. So sound propagation. So how is the sound planted forth? How is the sound produced? How is the sound energy given on to the next one? Okay. Right. Okay, so I'm going to explain this. And then I'm going to explain the formula that goes with it. Okay? The change in frequency is, we said, you hear pew, pew, pew. Okay, so what change do you observe? Why do you observe a change? Because either the sound source and or the listener moves. The car is coming towards you, you are moving away from something. So we move, we have different velocities relative to the speed of sound. Okay, we have a different velocity to the speed of sound. So because there's a different velocity between the two, there's a change in frequency that is observed. Okay, that's what the definition means. So the whole thing that I've explained to you from the beginning of this lesson, that's in this definition, just in very fancy wording. Go study it off by heart. They are going to ask it. Okay, now the formula that goes with it is this one on your data sheet. What is this? It's the frequency of the listener, the frequency that you hear. Okay, then we have, the speed of sound in air, or the speed of sound. Okay, 340. Speed of sound, 340. And then you have the speed of either the listener or the source. The listener is the person hearing it with their ear. The source is the person making the sound. Okay? And then we have the frequency of the source. The ambulance or you or the whatever making it. Okay. So that is all in the formula. You can see it's plus, minus, because it depends whether you are coming towards or whether you are going away. Because we know now that if you come towards, then it will be higher pitch. If it goes away, it will be a lower pitch. Okay, so we must know, sometimes we must plus, sometimes we must minus. Okay, now we're going to look at when do we do what. Okay, here is my summary for you. In the alphabet, which one comes first, S or L? L. So if L is in front of S, then it is a plus, then it's sharp. That's correct. If S is in front of L, it's wrong, then it's a minus. Okay? But what does this stand for? What does it mean? We're going to have 4 scenarios. Either you can have your car, let's make this a siren. Either you have your car coming towards you, standing there. Right? So you can see here, the source comes towards the listener. The source comes towards the listener. Then it is that first one. So the ambulance or the whatever is coming towards you. Source coming towards the listener. Then it's a negative. Or there is a house and someone broke into the house and now they are running away. Oh, yeah, no. Okay, that's some skill. Did you try that? Okay, they're saying, oh, don't catch me. So the listener, you with your ears, hear that the source, the house, the alarm goes off. Pew, 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 whatever. Okay, so the sound source is stationary and the listener is moving away from it. Then that is also the first scenario. Then you would substitute in a negative. Okay, are you with me? The other scenario that we can have is, let's say you have someone standing there and this car is driving away from them. Okay, so we have our listener there and our source there. So you can see there, the source moves away from the listener. So it's in that direction. Listener, source, that direction. L comes before S in the alphabet. So it's the positive one, that one. When will a listener come to a source? Are we saying the policeman is rocking up to the house? That's making the alarm? Okay, so we have the house that makes the alarm, the source, and now the police car is coming towards it. So the policeman is inside the car and he's coming towards the house. That siren is going off. Because he maybe wants to catch the person off guard. Okay, so you can see here the listener comes towards the source. Listener towards the source. So that is why it's also a positive. Okay, so yeah.
What would be the case then, say like now both are making a sound?
Yeah, so they can both make a sound. Depends on how loud the sound is. If the policeman's car is also going, do you think it will hear the sound of the house? Not necessarily. But if he focuses on the sound of the house, he might hear a change in frequency. But yeah, so it depends. Alright, so you see that we can have 4 scenarios. And just like in the previous chapter and the chapter before that and the chapter before that, chapter before that, what must you do to help to assist yourself? Draw a diagram so that you can see, is the thing coming towards or is it going away? What's happening? Alright, let's see how we're going to use this. It says, a train passes a conductor standing at a station at 22 meters per second. So what is a conductor? The? No, so it can be, but it passes a conductor standing. Okay, so the train conductor, so it's maybe another train conductor, whatever, the person that, he can drive the train, he can regulate the train, he can watch the coming in and the coming out of the train. He has a lot of jobs. Okay, so we have there, there's the railway. Oh, I think I wanted to change the wording there. Oh, okay, yeah. So the train passes. Okay, that's the key word there. So let's say my train, there's my train. Oh, here, I need to know how to draw this. Okay, there goes the train, and there is my conductor. Okay, so the train has passed the conductor. Okay, the speed of the train is 22 meters per second, they tell me. The train driver sounds the hooter, toot toot, which has a frequency of 250 hertz. So the frequency, is the train the source or the listener? The source. So the train is the source and this is the listener. And the frequency, so the train has a hooter that has a frequency of 250. So the frequency of the source is 250 hertz. What frequency will the conductor hear? So they want to know what is the frequency of the listener. Okay, now subconsciously they gave us a lot of other information as well. They say the conductor is standing. So what is the velocity of the conductor? 0. And the conductor is the listener. So the velocity of the listener is 0. And the velocity of the source of the train is 22. They gave that to us. Okay. So we're going to write down our formula exactly like it is given on our data sheet. Okay, now we need to, yes. When we substitute our values, we're going to choose is it a plus or a minus. Okay, right. Now let's just quickly see. Now, before I put in my plus and minus, I'm going to put in my values. We're going to take the speed of sound to be 340. So we're taking that to be 340. 340. The velocity of the listener is 0. And the velocity of the source is 22 times 250. You already asked me that, didn't you? No, you want to ask me that. What did I say? It's not always that. Okay? They should tell you what you can take the speed of sound as. Alright, now, we see there that the source is moving away from the listener. Okay, so which one is that? The source is moving away from the listener. Is that one? Is L before S in the alphabet? Yes. So it's a plus. Okay, now where must you fill in that plus? You fill in the plus there where you have a value. You fill in the plus. So there you're going to say plus 22. And there where you have a 0, even though it won't make a difference, there you put in a negative. Alright, and if you fill that in, it gives you 234.81 hertz. Yes. No, it won't make a big difference, but getting to university, they might ask you that. Alright, I just want to check if I wanted to give you homework. No, I didn't. Alright, enjoy your day.